Today we'll discuss a simple system that many of us may already be familiar with. It'll turn out to be a simple first order system, and we'll try to build a mathematical model of it. I'm talking about a fidget spinner. These spinners, many of you might have already seen or played with. It's a toy that's become pretty popular these days. It's just a simple device where you hold it in the middle and try to spin it as fast as possible and for as long as possible. These spinners, here are some of the spinners that we have in the lab. These exist, they're all sort of made in different ways, and most of them have multiple prongs that are attached to it. And they also have these internal bearings that we will just take a look at. They have a bearing on the inside over which it spins, and sometimes these and depending on the quality of the bearings, the spinner might spin for longer or not as long. So we'll look at how to build a mathematical model of the system to see how we can understand its behavior, and specifically how the bearing impacts the motion of this. In this case, we'd like to know what is the angular velocity of that system. So let's consider our fidget spinner. This is sort of my graph of a fidget spinner that is spinning about an axis over its center. The angular velocity is omega. And there's a bearing here inside this over which it spins. And this bearing causes a friction that causes the spinner to eventually stop rotating. Let's call that bearing friction B. And because of this, and the bearing friction, the torque, the reaction torque the bearing produces will be B multiplied by the speed omega. Okay. So just like we looked at the previous problems, or the previous one, so let's look at, if we apply some initial torque tau sub I, what would be what would conservation of angular momentum tell us? The sum of all the torques acting on this body. Oh, and this body has fidget spinner has a moment of inertia J, will be J omega dot. And what are torques acting on it? We have our input torque. We have the torque caused by the damper, which would be opposite to the input. So we have J omega dot plus B omega equals tau sub I. Okay. Now tau is the input torque, but we don't apply a constant input torque. We apply a pulse input or an impulse. So that is 0 for most of the spinning of the damper. So what we can assume here is that instead of applying an input torque, we start off with the angular velocity at point 0, that is some initial omega 0. So instead of applying initial torque, we're giving it an initial angular velocity, and the torque is 0 after that. We don't really need to make this assumption to solve this problem, but it does give us a simple way of finding the solution pretty quickly. So J omega dot plus B omega would then be equal to 0, since this is 0 except for the initial impulse. And we've seen the solution to this again. So we can write down omega equals A e to the lambda t, right, and substitute that in there, and we can solve that equation. And you can consult a previous video to look at the solution to that. We would end up getting omega equals A e to the minus B over J times t. And if my initial velocity omega 0 equals is omega 0, the final equation I would end up getting is a omega 0 e to the minus b over j times t. So this is a first order response with a time constant of tau, which is just j divided by b. So this tells us a few things. So let's try to graph it to see what it looks like. So this curve makes sense to us because initially we have an omega 0, and over some time the angular velocity would go down to 0, and at the time constant would be given by j divided by b. So j is the moment of inertia. So this tells us for these devices, if they have a very high moment of inertia, so if we have a very high moment of inertia, that means the mass would be distributed at some large radius around it. So that's why you usually see them with these prongs with masses, like fairly heavy masses on the outside, that to boost its moment of inertia. We have to reduce the damping also. So the damping is low, we get a higher time constant, so it will take longer for this curve to reach 0. So this sort of gives us a little bit of a hint as to how to design a simple fidget spinner. It's a simple first order system that we can understand pretty quickly. We also can get the curve that it represents this angular velocity versus time. Thank you.